Okay, so this is our first of several lectures regarding amplifiers. So I'm going to call this one an introduction to amplifier circuits. And I am going to ask you guys, if at all possible, and this shouldn't be a big ask, to forget everything that you learned about op amps and circuits one, which we only covered it for 2 days and most of you guys struggled with it, so that shouldn't be that big of a thing to forget all of that stuff prior. Okay. So I'm going to start by drawing a terrible picture. So let's say that we have a time varying signal. Okay. Just for the sake of argument, I'm going to make it sinusoidal, but it doesn't necessarily need to be sinusoidal by any stretch of the imagination. And our signal right here in red could be representative of a voltage as a function of time, a current as a function of time, or a power as a function of time. And we want to transform this signal into a scaled version, okay? So I'm going to choose to scale this in such a way that it is larger than the original signal, but that doesn't necessarily have to be the case. So over here in blue, we're going to have what's hopefully just a larger version of our original signal, or something similar to that, like so, where this guy is also a voltage, current, or a power. There are pretty much two ways that we can accomplish this scaling of voltage, current, and power signals. One way is using amplifiers. We'll talk about the pros and cons of that. And then the second way is using transformers. We'll talk about the pros and cons of that. So circuits 2 starts off with a very in-depth discussion of amplifier circuits, and circuit 3, as it turns out, is going to start off with a very in-depth discussion of transformer circuits. So we're going to bring all of this together by the time that you guys wrap up your circuit theory classes. So let's start with amplifiers over here on the left, okay? So one of the key characteristics of an amplifier is that amplifiers are active devices, meaning that they require external power. And then over here on the right-hand side, we're going to contrast that with transformers, which are passive devices, meaning that no external power is required. And so that's one of the biggest differences. So there are some consequences to this that we'll talk about in a minute, but on paper, it might seem like a transformer is a better way to do things because it doesn't require any external power, right? So if I put a voltage across the input terminals of a transformer, I'm going to measure some voltage across the output terminal of the transformer, and it's only going to depend on the number of turns in the transformer windings and literally nothing else, right? So that's a nice and easy way to get voltages to be either larger or smaller. It just depends on how much we wrap a wire around something. Whereas with an amplifier, I have to literally apply external power. So the benefit of using an amplifier is that the output power doesn't necessarily have to be equal to the input power. And so what I mean by that specifically is that the signal power that we are trying to amplify can be larger at the output of our amplifier than it is at the input. And it's because we require this external power that allows us to do that. We're effectively taking power outside of our system and using it to boost our signal levels through the use of an amplifier. Whereas with a transformer, our output power in an ideal case will be equal to our input power, but for any real transformer, our output power will be less than our input power because the wires that form the coils of our transformers have resistance and therefore cause ohmic losses, okay? So amplifiers are used when we want to be able to boost the power levels of our signals as well as either the voltage or the current. Transformers are used when we are just worrying about increasing the magnitude of the voltage or increasing the magnitude of the current, and the power level isn't necessarily a principal part of our consideration. Okay? So that's the different applications for doing effectively the same thing, making these signals look larger and smaller. Okay? So more formally, an amplifier is an electrical circuit or device which increases the magnitude of the signal applied at its input. So if we think of an amplifier as a black box device where our input signal is applied to this left-hand set of terminals, so this is going to be a black box amplifier. I'm going to quantify my input signal as X of t over here on the left-hand side and Y of t over here on the right-hand side. Then how this guy works is that our output signal Y of t is a scaled version of our input signal X of t. The scaling factor A is more commonly called the amplifier's gain. Sorry, that scrolled way too far. And what this gain really represents is the transfer function of the amplifier circuit as a whole, right? So we can think of an amplifier as a device that's acting on our input signal to produce an output. And that's what this represents here. And so we have a transfer function that acts on our input, giving us our output Y of t, which is just a scaled version of our input signal. Now, there are multiple different types of amplifiers and multiple different ways to classify amplifiers. And so we're going to talk through some of the most basic configurations today by quantifying them in terms of their input signal and their output signal. Okay, so I'm going to make a little table here. Inputs will be on the left-hand column. Outputs will be on the right-hand column. And then the name will be over here in the far, or I guess output will be in the middle now. The name of the amplifier will be over here. Right? So what we are familiar with to this point would be a voltage at an input. So if we apply a voltage at an input and measure the voltage at an output, we have, unsurprisingly, a voltage amplifier. This is what an op amp is. If we have a current at the input, measure a current at the output, unsurprisingly, we have a current amplifier. This is what some configurations of transistor amplifiers do. If we apply a voltage at the input and measure the current at the output, we have a transconductance amplifier. If we apply a current at the input and measure a voltage at the output, we have a transimpedance amplifier. And lastly, if we apply power to the input and measure power at the output, we have a power amplifier. We could also go into class A amplifiers, class B, class AB, and all that kind of stuff. And all that'll be covered when we talk about transistor amplifiers and all that kind of jazz. So where do you guys think we might see amplifiers in our everyday lives? Music. Okay, so that's definitely one place that amplifiers are used. If any of you guys have been to my office, probably know that I'm an electric guitar nerd. I have, I think, currently 9 guitars total, 2 in my office, 7 at home. And so I'm always looking for new guitars, new amps, and all of that kind of good stuff. So that's definitely a place where we'll see amplifiers. Interestingly enough, actually, if we think about the amplifier used for electric guitar, it's actually composed of multiple amplifiers. So there's a first stage, which is called a preamp stage. And in that preamp stage, the signal from our electric guitar, which is usually on the scale of millivolts, is converted into a larger voltage signal that is then passed into the power amplifier stage. So the preamp stage is a simple voltage amplifier because we have voltage in, voltage out. The power amplifier is needed at the output stage is because we're trying to drive speakers, and speakers have mass. And so just using a voltage without having a supplemental amount of necessary current isn't going to be able to physically move those speakers around. So we're not going to really be able to hear anything. So we need a power amplifier to give us enough push to drive large speakers that have physical mass, right? We have similar setups in our cell phones and things like that, right? How many of you guys have taken Physics 202? So a handful of you have taken Physics 202. How do electric fields behave the further away from their source you are? So let's say that we had an electric field that is being supplied by a cell phone tower, right? And we are far away from a cell phone tower. What's happening to the electric field strength as we get further away from that cell tower? It's going way down, right? The electric field strength is dependent on the square of our distance away. So we need a voltage amplifier in order to increase the signal to a point where our processors actually do anything with it. I'm going to close that door because the ELEN is going to distract the hell out of it. If it gets uncomfortably warm, we'll open the door back up in a couple of minutes after all those people leave, right? So amplifiers are used literally all around us. Every single person in this room most likely has at least a handful of amplifiers in their pocket because of having a cell phone. If you have your wireless speakers in your pocket like I do, you've definitely got more amplifiers and all that kind of stuff in there. If you drive a vehicle, there are amplifiers and all of that for your regular radio, satellite radio, all of that kind of good stuff. So amplifiers are literally all around us. Okay. So let's consider a simple representation of a voltage amplifier circuit. We're still going to be using a black box here. Okay. So on the left-hand side, I'm going to have a practical voltage source because in real systems, our voltage sources have some internal impedance that we need to account for, right? So here's my voltage source, Vs of t, and my source resistance, Rs. This big box here in the middle is my amplifier. And on the output side of my amplifier, I'm going to connect a load. And for our intents and purposes, this load will be resistive. So I'm going to subdivide this circuit into three distinct portions. On the left-hand side is our source portion of our circuit. In the middle here is our amplifier. And on the right-hand side is our load. And now I'm going to identify some signals, right? So across the input terminals of our amplifier is where we're going to see the voltage Vn. And this is going to be different than Vs, right? So the voltage that the input terminals of our amplifier sees is going to be different than our signal voltage because we have some resistance in our system. So it's going to look to some extent like a voltage divider, and we're going to have a smaller amount there. And then over here, on the output terminals of our amplifier is where we're going to define the out. And then explicitly across our load resistance, we are going to have our load voltage, ELEN. For a simple resistive load, these two things should be identical, but we could have a more complicated load where the voltage seen across these terminals would not be equal to the voltage drop seen across our load, okay? So the desired or ideal behavior of this circuit is that VL of T, our load voltage, will be a a scaled version of Vs of T. So ideally, VL of T is just our amplifier's gain times Vs of T. And in a couple of days, we're going to talk about what specific criteria needs to happen in order to accomplish this. But for today, we're going to work on developing a model that will help us wrap our head around how these things work. The reason that we're going to use a model is because the internal circuitry of an amplifier can be extremely complex. I'm going to open up a file here. For those of you that took me for Circuits 1, you've already seen this. Here we go. So this is the data sheet for a Texas Instruments MU-A741 op-amp. Okay. Let me scroll up here so you guys can see it. This is a simplified representation of the internal circuitry of an operational amplifier. We can see from this little table down here that this simplified representation contains 22 transistors, 11 resistors, a single diode, and a single capacitor. analyzing this thing would be an absolute terrifying nightmare, which realistically, by the time you're seniors, you would actually be able to understand most of it. Right now, not so much. So instead of looking at this big, ugly thing, we are going to develop a simple model based on some information that's usually provided in our data sheets for an amplifier. So if we were to scroll up to our electrical characteristics, we can see that there are certain things that we're given, like offset voltages, offset currents, input voltage range, input resistance, output resistance. Where's the gain on this bad boy? We're on a different thing. So let's go up here. Yeah, there we go. Thermal information. I know it definitely tells me the gain somewhere. I'm just not seeing it. There we go. AVD, large signal differential voltage amplification, right? So we're told input resistance, output resistance, and large signal differential voltage amplification. It's kind of grainy to see right here, but if we look at our large signal differential voltage amplification for this particular amplifier, the minimum value is 20 volts per millivolt. So the differential voltage gain provided by this particular amplifier at a minimum is 20,000. A typical value is 200 volts per millivolt for 200,000. But this value is going to change from sample to sample. And that has something to do with how difficult it is to manufacture integrated circuits and all of that kind of good stuff. So typically speaking, for an op amp, we're going to see voltage gains of somewhere in the ballpark of hundreds of thousands. Okay, so we'll talk about that in a little bit. If we look at our input resistance here, minimum value 0.3 mega ohms, typical value somewhere in the ballpark of 2 mega ohms. Our output resistance, typical values are in the ballpark of 75 ohms, all that kind of good stuff. These are the three parameters that we can actually classify damn near every amplifier we are ever going to deal with, regardless of how complex it is internally. We can classify it just using input resistance, output resistance, and voltage gain. So I want us to figure out kind of why that is really quickly. So if we disconnected our source side of this thing and looked in, what do you think we would see? So we are effectively looking for a Thevenin quantity by disconnecting all this stuff over here and looking in. Since we don't have our source connected anymore, I would argue that we're looking at a dead network, right? What do we see when we look into the terminals of a dead network? Thevenin resistance, absolutely right. So we're going to see some resistance. That resistance will be our input resistance because we're looking in through the input terminals, right? If we disconnected our load and looked in, what would we see? Well, we have a live network now, right? So what should we expect? Thevenin voltage in series resistance, right? Because we have a live network, we would see an entire Thevenin equivalent circuit, not just the resistance portion of it. Okay? So I'm going to redraw this circuit as follows. Okay. So our source side is going to be exactly the same. And our load side is going to be exactly the same. But what we see in the middle is no longer going to be a black box. It's going to be what's called the practical op-amp model. So we have some input resistance here, Rn. And as we saw a moment ago, this is usually given to us on the manufacturer's data sheet for a particular type of amplifier. This is still the input voltage terminals for our amplifier. And on the output side, we're going to see a Thevenin equivalent circuit. So it's going to be a voltage source in series with an output resistance. And I'm choosing to represent this voltage source as a dependent source. And the reason why I'm using a dependent source here is because I know that my output voltage, the out, could be a scaled version of my input voltage. So the input and the output are coupled to each other in some way. And I'm just describing that in the easiest way I know how with a dependent source. So this is going to look like AV, our voltage gain, times Vn of t. And this thing here in the middle is what's called our practical amplifier model. We are going to use this in this class a little bit while we get comfortable with understanding how amplifiers work. We're going to use this model extremely extensively in our later electrical engineering classes, particularly when we're designing amplifiers and trying to see what changes happen when we add resistances and capacitances and all that kind of good stuff. So this is our practical amplifier model, and it is characterized by these three parameters: R in, R out, and our voltage gain AV. So we are concerned with operational amplifiers in this class. And so we're going to have to modify this model very, very slightly. The reason we have to modify it slightly is because in an op-amp, we have two input things, right? We have a non-inverting input and an inverting input. And as it stands right now, we only have access to one input with respect to effectively ground, the negative polarity terminal of our source voltage. So our op-amp practical model, scroll here, I misspelled practical. Is as follows. So this pin is for our non-inverting input voltage, which I've labeled as V+. Okay. Made that too low. This is our input resistance Rn. And this terminal is for our inverting input voltage, which I'm going to label as V minus. So V plus is for the non-inverting input terminal. V minus is for the inverting input terminal. And the voltage drop across this input resistance is what I'm going to call a differential voltage. Our differential voltage VD is going to be defined such that the positive polarity terminal is at the non-inverting input and the negative polarity terminal is at the inverting input. And this is always going to be the definition. Positive polarity goes with the non-inverting, negative polarity goes with the inverting. Okay. We might draw this differently, but VD's definition will always, always, always be the same. Okay. On the output side of things, we're going to have our practical voltage source that contains our dependent source right here. And I'm going to call the gain AVOL. Okay. So the V is because this is a voltage gain, and the OL stands for open loop. Okay. So open loop voltage gain. And that's that information that was provided to us on our data sheet, typically on the ballpark of hundreds of thousands to millions for some op-amps, okay? So it's very, very large quantity. And instead of just having VN, we're now going to have that differential voltage VD. Here is our output resistance R out, again, typically provided on our data sheet. I'm going to ground this central terminal. And so this is the output voltage pin measured with respect to ground. Okay. So all of our voltages in this circuit can be thought of as nodal voltages because they're all going to be measured with respect to ground, which is what we were doing way back in circuit points. So this big ungainly thing right here is how we are going to represent our simple triangular model that we're used to. So I want us to work quick examples using a practical op-amp model to actually show you guys one of its biggest limitations. So let's say that we have the following circuit. We're going to apply 1 volt directly to the non-inverting input terminal. We are going to ground the inverting input terminal. And we're going to measure our output voltage with respect to ground. Now, because we know our amplifiers are active devices, meaning that they require external power, I'm going to explicitly show our power supply voltages in this diagram as well. So we're going to have a voltage, let's call it VCC plus, of positive 10 volts, and a voltage of VCC minus that is negative 10 volts. And this particular amplifier is going to be characterized by an open loop voltage gain of 100,000 volts per volt, an input resistance of 1 mega ohm, and an output resistance of 25 ohms. I'm going to redraw this schematic diagram using our practical op-amp model to give you guys an illustration of how it's done. And then we're going to analyze our circuit. Our goal is to figure out what the output voltage of our system will be. So if I were to redraw this circuit, I'm going to start with the practical model by itself. So here's my non-inverting input terminal, my resistance Rn, which is 1 mega ohm. Here's my voltage, my inverting input voltage V minus. My gain is 100,000, so I'm going to call that 10 to the 5 times VD, where this is my voltage VD. Here's my 25 ohm output resistance. You guys got a question? If so, please ask. Yes, 1 mega ohm for the input resistance, 25 ohms for the output resistance, 10 to the 5 or 100,000 for our open loop voltage gain. All right, so this is our practical model. Now we need to connect them, right? Because we have external things connected to our op-amp. So our inverting input node was connected directly to ground, right? When we scroll up here, we can see that. Our inverting input was shorted to ground. So I'm literally just going to short my inverting input to ground. My non-inverting input, there is a 1 volt source between that non-inverting input terminal and ground. So I'm going to put a 1 volt source here between the non-inverting input terminal and ground. My output was just measured between that output terminal and ground. There was no load resistance or anything like that. So this is how I would properly represent that original schematic diagram using the practical op-amp model. Okay. So now let's analyze this thing. It should be fairly obvious to see that our output voltage here, V out, is just going to be 10 to the 5 times VD, because no voltage drop is going to occur across our 25 ohm resistor because it's not part of a closed current carrying loop. Right? So I'm going to write out here to the side, V out is equal to 10 to the 5 VD. Which begs the question, what is our differential voltage VD? Walter, you have any thoughts? Okay. Christine, way in the back, do you have any thoughts as to what VD would be in this case? Okay. So positive polarity terminal of VD is here. Negative polarity terminal of VD is here, which is at ground. So I would argue that this voltage VD is just 1 volt, which is the positive polarity terminal is associated with the positive polarity terminal of the 1 volt source. The negative polarity terminal is at the same node as the negative polarity terminal of the 1 volt source. So I think it's pretty reasonable for us to say that VD is 1 volt based on this schematic diagram. Anybody have beef with that? All right. So VD is 1 volt. So from that, what's V out? Ten to the 5 or 100,000 volts. I'm going to put a question mark and an exclamation point because that seems damn ridiculous, right? This is absolutely what our model is telling us, but does this seem practically possible? Not at all, right? If this were true, effectively op-amps would be sources of infinite voltage all over the place, okay? So what we are not taking into account here is the limitations that our power supply provides. Okay. So in a real op-amp circuit, the output voltage cannot exceed the power supply voltage. This phenomenon is what we call saturation distortion. We'll talk about it here in a moment. So while our model tells us that we should be having 100,000 volts on our output, realistically, we would actually just have 10, because that's what our positive power supply voltage is. So in this particular case, let me scroll back up here. Since our positive power supply voltage is 10 volts, our output voltage can never be more positive than 10 volts or more negative than negative 10 volts, because these are the constraints that define what our allowable output voltages are. Right? Technically speaking, this is only true for what's called a rail-to-rail op-amp. And we are going to consider every op-amp in this class a rail-to-rail op-amp, just for easiness of sense. Realistically, for a non-rail-to-rail op-amp, we would see that we actually have somewhere between a half a volt to a full volt of headroom loss near the positive supply voltage and a half a volt to a volt of headroom loss near the negative supply voltage, meaning that it would really be constrained to somewhere between 9 and 9.5 volts up here and negative 9 to 9.5 volts down here. It just depends on how the op-amp is designed and all that kind of stuff. It's literally somewhere on the data sheet tells you whether or not it's rail to rail or not. But we are going to deal with just rail to rail because they're easier to model. Just something to consider. Okay. So let's quantify this concept of saturation distortion. Okay. So our output voltage, V out, I'm putting it as a function of time, but that's not important, so I'm going to get rid of that, is going to be a piecewise function. Okay. So our output voltage will be VCC plus our positive power supply voltage when AVOL times VD is greater than or equal to VCC plus. And we call this positive saturation. So let's talk very quickly about what I mean by this concept of saturation. So in electrical engineering, we consider something to be saturated when an increase in a quantity doesn't cause a corresponding, so an increase in the input quantity doesn't cause a corresponding increase in the output, right? So if VCC were 10 volts and we were at the product of AVOL times VD were 9.9 volts, we would not yet be in saturation. But if we increase that voltage VD by a little bit, we would then hit VCC, and if we went any further, our output is constrained to just VCC. So we consider our output voltage to be positively saturated, meaning that it's just pinned to the positive supply voltage. On the opposite side of the spectrum, we have VCC minus as our output voltage, which will be true whenever AVOL times VD is less than or equal to VCC minus and this is negative saturation. And then we have the middle case, right? So our output will be our open loop voltage gain times VD when VCC minus is less than AVOL times VD is less than VCC plus. And this is the linear range of operation. It's in this linear range that our amplifier is actually acting like we would consider an amplifier. And our output is just a scaled version of our input. So what I want us to do now, and this will be, I think, the last thing that we're going to do today, is I want us to figure out what the linear range of this amplifier is. So effectively, I want us to figure out what the allowable input voltages are for this thing, right? We're going to use those numbers, a voltage gain of 100,000, R in of 1 mega ohm, which really doesn't matter right here, R out of 25 ohms, which also really doesn't matter right here. Okay. So our linear range is simply going to be VCC minus divided by our open loop voltage gain will be less than our differential voltage, less than VCC plus divided by our open loop voltage gain. I'm going to call this here the linear range of our amplifier. What happens if we put numbers to this, right? What was VCC minus? Negative 10. So negative 10 divided by 100,000. A negative number, sure. Negative 100 microvolts. And then on the opposite side, since VCC plus was equal to in magnitude of VCC minus, we'd have positive 100 microvolts. So that means that if we wanted to actually use this amplifier in this particular configuration to boost a signal and have the output be a scaled version of the input, our input signal has to lie somewhere in this range. Otherwise, we're going to hit saturation. This is a very narrow window, right? Negative 100 microvolts and positive 100 microvolts. That's very, very, very small. Okay? Typically speaking, operational amplifiers are not used in an open loop configuration because of this. Our linear range is so small that we can't really use it as an amplifier in this configuration. So what we're going to talk about in our next class meeting is certain applications where having practically no linear range is actually a good thing. And those amplifiers are called comparators. Okay, so we're going to start with a practical look at applications of op-amps using open loop configurations. That'll be Monday. Then we're going to talk about feedback and go over positive feedback applications on Wednesday. And then we're finally going to get to negative feedback, which is what everything we learned in Circuit 1 had to deal with. And we'll talk about those applications for the remainder of the time that we're talking about op-amps. All right. Unless anybody has any questions, I will see you guys on next Monday. I hope you have a great weekend and all that kind of jazz.